Hello friends, welcome back to my channel. Let's begin our new video with a new topic, that is Green's theorem. Green's theorem is a fundamental result in vector calculus that provides a relationship between a line integral around a simple closed curve and a double integral over the region bounded by the curve. Let C be a positive oriented, piecewise smooth, simple closed curve in the plane, and let D be the region bounded by C. If F is equal to P, Q is a vector field whose components P and Q have continuous partial derivatives on a open region that contains D, then phi p dx plus q dy is equal to double integration of dou q by dou x minus dou p by dou y dA. See the applications of Green's theorem. Rendering and shading. Green's theorem helps in calculating areas and centroids which are crucial for rendering and shading processes. Texture mapping, used in algorithms that involves the integration over surfaces, essential for applying textures to complex shapes. Mesh generation and processing, helps in operations like mesh smoothing and mesh simplification by providing a mathematical framework to handle the geometry of the surfaces. Robotics, path planning, used in computation of potential field and navigation function for robot path planning. Motion control, assists in integration of movement equation over a region crucial for controlling the movement of robotic arms and autonomous vehicles. Next application is computational geometry. Area computation. Efficient algorithms for computing the area of complex polygons and planar regions often use Green's theorem. Curve analysis helps in analyzing properties of curve and surfaces, such as determining whether a point is inside a polygon. Numerical analysis. Finite element method, FEM. Green's theorem is used in the derivation and implementation of FEM, which is widely used for solving partial differential equations. Boundary element method, BEM, utilizes Green's theorem for converting domain integral into boundary integers, signifying the computation in problems like fluid dynamics and electromagnetics. Computer vision, image segmentation. Green's theorem is used to compute properties like area and centroid of segmented regions. Shape analysis and recognition, assists in extracting features from shapes, which is fundamental in obtaining recognition and classification tasks. Electromagnetic simulation, field computation, used in simulation of electromagnetic fields by converting volume integrals into surface integrals, simplifying the calculations. The next type of application is data visualization. Flow visualization helps in visualizing vector fields such as fluid flow by providing a mathematic basics of integrating and interpreting the fields over surfaces. Algorithm optimization, Reduction of computational complexity. In some algorithms, Green's theorem can simplify the computation by reducing double integrals to simple integrals, leading to efficient algorithms. Let's see some advantages of Green's theorem. Simplification of calculations. Transforming line integrals to area integrals. Green's theorem can convert a complicated line integral around a closed curve into more manageable double integral over the region it encloses. This can simplify the computation significantly efficiently when dealing with complex boundaries. Simpler computation for certain regions. For certain geometrics, it can be easier to perform a double integral over the area than to perform a line integral around the boundary. Geometric and physical insights. Area computation. Green's theorem can be used to find the area of a region by converting the boundary integral into double integral. The particularly used in computer graphics and computation geometry. Centroids and moments of inertia. The theorem can help in inertia of finding centroids and moment of inertia for planar regions by simplifying the integrals involved. Let's see some disadvantages of Green's theorem. Requirements on the curve and region. Simple closed curve. The theorem requires the curve C to be simple closed curve. This excludes curves that inserts themselves are not closed, limiting the type of regions that can be analyzed. Piecewise smoothness. The curve C must be piecewise smooth, meaning it can be composed of a finite number of smooth segments. Highly irregular or fractal-like boundaries are not suitable for direct application of the theorem. Continuity and differentiability. Continuous partial derivatives. Green's theorem requires that the function p and q have continuous partial derivatives in region D. This excludes vector fields that are not sufficient smooth or have discontinuous in region. Region requirements. The region D must be simple connected, the meaning cannot have holes, or regions with holes. The theorem need to be applied separately to each simply connected subregions, which can complicates the analysis. Thank you for watching this video. Please like, share and subscribe.